explore what is a series. So series and sequences often get confused with the language, and they do build off of each other. So a series is the sum of the terms of a sequence. So we take a basic sequence, so a list of values, and you add them all up. And then there are two different kinds of series that we can have. We can have a finite series where we know the first and last term, or we can have an infinite series. So in other words, it continues on indefinitely. So a finite series notation, right, we're going to use sigma notation, summation notation for these. So a finite series example might look like this. The sum from n equaling 1 to 5 of, I don't know, 2 plus n over 3n minus 1. An infinite series, however, goes on forever, so we don't know what term it stops at. Right, so I can take the same sigma notation, right, the same sequence, but now it goes to infinity instead of 5. Right, so this is our sum, so that tells us that it's a series, and then this is the sequence that we're taking the sum of. So that's really the only difference between a series and a sequence. A series is just the sum of a sequence, so you're still building off of all of your sequence knowledge. So then we have something called partial sums when it comes to series. So for a finite series, we can always find the value. We can always find the sum of a finite series, but we can't always do that for an infinite one. So for an infinite series, we're often going to create a new sequence of something called partial sums. So this means that we're going to find the sum of a sequence of finite series and look to see if there's a pattern. So remember, for an infinite series, we're looking at something like this. So we're just going to use the sum from 1 to infinity of some sequence an. So our partial sums are you just take a specific number of terms of the sequence and add them up. So if I ask you for the first partial sum, we're going to call that S1. That's just going to equal the first term of the sequence. Right? S2 is the second partial sum. I'm going to add up the first two. Right? And let's make this a little better notation-wise. Let's connect this back to our summation notation, right? This is really the sum from n equaling 1 to 1 of a sub 1, and that's going to equal a sub 1. Sorry, a sub n in here. Whoops. Right, this is the sum from n equaling 1 to 2 of a sub n, and that's going to equal a sub 1 plus a sub 2. Right, we can continue that pattern on. So S sub 3 is the third partial sum. You would take the sum from 1 to 3, so I would add the first 3 terms up. Right, so S sub 4 is then the fourth partial sum, so we're going to add the first 4 terms. Got a little stumbled over those words, right? And then we can take it out to, this is called the nth partial sum. And that's the sum from n equaling 1 to n of a sub n. Right, so that's a1 plus a2 plus a3 plus dot 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 plus some value a sub n, and n is out like really far. We don't know what it is. So we're going to start by looking at some partial sums today and then building up to what that means for the overall sum of an infinite series. So the first thing we're going to look at is actually finding partial sums for two different sequences. So we have two sequences below, a sub n and b sub n. And we are going to find, got caught up a little bit. So we are going to find the sequence of partial sums S1, S2, S3 got cut off out to Sn, and then we're going to determine from those if we think these converge or diverge. So I'm actually going to show you how to do this with your calculator too. Right? So some of these aren't too bad. So we're really looking at the infinite series here. So we're going to look at the partial sums. So we got S sub 1 first, and that's just going to equal a sub 1. So that's going to be 1 over 1, which is 1, right? We've got S sub 2, right? So that's a1 plus a2. So that's going to be, well, we know a1 is 1, plus if I plug in 2, I'm going to get a half. So that's going to be 3 halves, right? S sub 3, right? That's going to be the first three terms. So that's going to be 1 plus 1/2 plus 1/3. So I got 3/2, right, plus 1/3. So maybe I don't want to do all the fraction math in my head. So let's show you how to do it on a calculator as well. So I have my calculator in sequence mode, you can see. You can have it in any mode, the function mode, parametric, polar, or sequence. To do this, it doesn't matter. It's just going to change which variable on your variable key you're using. So if you want to do a summation for a finite number, there's two ways of getting your sigma notation up. You can go to the math key and go down to the 0 option. Then you can see it says summation. I'm going to click enter there. You can also pull it up if you hit alpha window, and then you can see that it's option number 2 there. So then I want to take the sum from n going to 1, and then I want the third partial sum now, so I'm going to go to 3, and then I'm going to put a fraction in here, and I'm going to put in 1 over n. Right? And I want to make it automatically a fraction, so I'm going to do math fraction there, and that tells me that my third partial sum is 11 over 6. Right. Good. Right, so if I wanted to do S sub n, that's going to equal 11 over 6 plus, right, 1 over n. Right, and we're doing all of the terms in between there. So we would be adding 1/4, 1/5, 1/6, whatever. So now we want to kind of figure out, do we think this is converging or diverging? So maybe we want to look at some other partial sums. So we're going to use the calculator to do these. Let's find S100, S1000, right, and S10,000. So the easiest way to do this is if I go back to my calculator, I'm going to go up and copy this, and all I'm going to do is change that top number on my sigma. So I'm going to make that 100 now. And it's not even going to come up as a fraction anymore because the number is going to be too big. Okay, so S100 is 5.187. Okay, so now if I do that again, copy that down, hit 0, see how long it'll take it to think, right? We've got 7.485 now, just rounding to 3 decimal places. You can also copy stuff down by doing second enter. That's my typical, because my physical calculator doesn't do the copying things. Or if you have an older TI-84, it won't do the scroll up and copy down. And then let's see here, it's going to take a second because this is a lot for the calculator to do, right? It's 10,000 additions, so it's going to take some time. Give it like 10 more seconds and then we're just going to move on. Nope. Okay, so going back to the screen, I wrote down the first two, right? So we don't know what this is yet, but we can kind of see that S100 and S1000 are pretty different numbers. So if we think back to when we did improper integrals, we can kind of tell that that's not going to converge. So that means that we can say that the sum from 1 to infinity of 1 over n is going to diverge. Right? Because it's not going to consistent number. The sum is not balancing around a constant value. So we're going to do the same thing now, but now we're going to do 1 over n squared. So we're going to do S sub 1, that's 1 over 1 squared, that's still 1. Right? S sub 2 would be 1 plus 1 over 2 squared, which is 4. So it's going to be 5/4. Right? S sub 3 is going to be 1 plus 1/4 plus 1/9. Okay, I don't want to do that fraction math in my head. Okay, oh, and my calculator just finished it, right? That's 9.788, so we'll just put that on there. Now we know it's definitely not converging, 9.788. And then go back to the calculator. Okay, so I'm going to use the alpha window trick, option 2. So that's n equaling 1. Oops. And then I want to go to 3, and then we're doing a fraction of 1 over n squared, and then I want to set my calculator up to give me a fraction answer if I can. Okay, so that's going to be 49 over 36. I can also look at that as a decimal, right? That's right, 1.361. And we know what 5/4 is, that's 1.25. It would help if you guys could see, where's my mouse, what I'm writing, right? We can see that now on the right-hand side of the screen. Right, so S sub n would equal, right, 1 plus 1/4 plus 1/9 plus, right, 1 over n squared, right? So again, we want to now determine if we think this is going to converge or diverge. So let's do the same thing. Let's look at just S100, let's look at S200, and then we'll jump up to S1000. We'll make it a little easier for the calculator to compute those values. Okay, so jumping over here, we're just going to scroll up and change that 3 to a 100. Okay, so that's going to give me 1.635. So not a huge jump between the S3, the third partial sum, and the 100th partial sum, right? 1.361 to 1.635. Okay, let's make that into 1,000. I'm sorry, I said 200 next, didn't I? So let's do 200. Okay, 1.6399, so 1.640. Okay, and now if I make that into 1,000, got 1,000 there. Right, so we can see between the 100 up here, the 200, and then 1,000, right, there's barely any difference. So that looks like it is tapering off to a specific value. So we're going to say that the sum, the series from 1 to infinity of 1 over n squared is going to converge. So it converges. Now, what it converges to, we're not exactly sure. But you can also think, right, think back to the p-series improper integrals, right? These reflect kind of that same pattern. Where they converged and diverged. Right, and that is going to pop up later on in our series unit. So let's look a little bit further. So we're going to look a lot at convergence or divergence of series, and a lot of times we can only say whether or not a series, an infinite series, is going to converge or diverge. Not all is necessarily what it will converge to. So we say that an infinite series converges if the sequence of partial sums, right, so that S1, S2, S3, S4, all the way out to Sn, if that converges to a number, just like we just saw with that second example. So in other words, if we take the limit of our nth partial sum, the limit as n goes to infinity of S sub n equals some number S, a limit, a finite number, right? So if that happens, we say that that limit S is the sum of the series. But if the sequence of partial sums diverges like it did in that first example, right, the numbers for like S100, S1000, S10,000, they're vastly different. They're not like flattening out along a specific line, a specific number, right? If that sum diverges, then the series is going to diverge. So that's really confusing. So let's look at some instances of when things converge or diverge. So we're not always going to be able to find the exact sum of an infinite series if it converges. A lot of the time, and most of the time, we'll only be able to say if it converges or diverges. But there's a couple types of series that we can find the actual sum of, and one of these is called a telescoping series, and you're going to see why we call it telescoping. So I'm telling you right now that this series is going to converge. So we're going to find the different terms of it. So we have 1 over n squared plus n as our sequence in there. And what we might think back to in terms of integration techniques, because summations and integrals are really closely related, right? A definite integral is just the limit of a series, of a Riemann sum, right? That looks a lot like the format for partial fractions. So we're going to actually break this down. So we're going to rewrite this because of partial fractions. Right, so I have 1 over, if I factor the denominator, n times n plus 1. So if I set up my partial fractions, Okay, that means 1 is going to equal a times n plus 1 plus b times n. Now if I set n equal to 0, I get 1 is equal to a. And if I set n equal to negative 1, I'm going to get 1 equals negative b. So negative 1 is equal to b. Okay, so if I break this apart now, if I take the sum from 1 to infinity, I can say that that sequence is the same as 1 over n minus 1 over n plus 1. Now let's actually start finding some terms. Right, so if I plug in n equaling 1, right, that's my first n value. 1 over 1 would give me 1, and then 1 over 1 plus 1 is 1/2. Right, and I'm finding a sum, so I'm going to be adding my terms together. So now if I plug in 2, 1 over 2 minus 1 over 2 plus 1 is 1/3. Okay. Right, plus, now n equaling 3. Right, if I plug in for my third term of this sequence, I'm going to get 1/3 minus 1/4. Right, and I'm going to find the first 4 terms here. So I'm going to do 1/4 minus 1/5. Right, plus dot, dot, dot. Right, it's going to keep going out forever. Right, plus, right, I get 1 over n minus 1 over n plus 1. Right, there's our nth term. Now, if we look back at the terms that we wrote, right, look, I have a negative 1/2 and a positive 1/2, so those are going to cancel out. I have a negative 1/3 and a positive 1/3, so those go away. Right, negative 1/4, positive 1/4, right, negative 1/5, and then the next term would have had a positive 1/5. So all of these terms are going to cancel out, which means that we're just going to be left with 1, right? That's the only thing that's left here that's not going to be canceled out. And if you think of, right, if we make this a little bit more formal, if we look at the nth partial sum, we would have that 1 plus 1 over n minus 1 over n plus 1, right? If we plug in n for our final term, and if we take the limit as n goes to infinity of s sub n, right, that's just going to equal the limit as n goes to infinity of 1 plus 1 over n minus 1 over n plus 1, and that's going to be 1 plus 0 minus 0, which is just 1. So the sum of this series overall is just 1. So that's called a telescoping series because if we break it apart, the different terms will cancel with each other. So think about like a telescope and how you can like push it in and it like collapses on itself. That's why we call it a telescoping series. The whole series is just collapsing in on itself, so just a couple of terms are going to be left. So I'm going to put another one up here. I'm going to ask that you try on your own. So go ahead and pause the video, see if you can break this apart, and then figure out what the sum of this is. This is also a telescoping series. Okay, so I'm hoping that you paused this and tried it. And if you did, here is the work for it. So when you break it apart, you should be able to break it into the sum from 1 to infinity of 1 over n minus 1 over n plus 3. And when you do that, right, if you break apart your terms, I wrote out the first 5 terms. The only numbers you're going to end up with are 1 plus 1/2 plus 1/3. And if you combine all of those together, you get 11 over 6. Okay. So another type of series that we can find the actual sum of is called a geometric series, and that goes right along with geometric sequences. So a geometric series is in that format of a times your common ratio raised to an exponent. And you can start the series at either 0 or 1. It just kind of changes how the exponent looks. So we can use that common ratio, which is that r value, to determine whether or not the series will converge. And that's called the geometric series test. So we want to know the names of our tests because it's really great for justifying our responses. So if we have a geometric series in either of those forms, whether it starts at 0 or 1, doesn't matter. If the common ratio, if the absolute value of the common ratio is bigger than 1, the series is going to diverge because you're going to be adding numbers that are bigger and bigger each time. If the absolute value of the common ratio is less than 1, so it's a number like 1/2 or 2/3, 5/6, something like that, the series is going to converge, and specifically it converges to this number. So that's a sub 1 over 1 minus r. So a1 is the first term in the sequence, so you plug in your starting n value, and then you divide that by 1 minus your common ratio. So we're going to look at a few of these to see how they work. So we're going to determine if the following series converges or diverges, and if they converge, we're going to find their sum. So now if we look at this, right, they're all geometric, right? They might not look like it right away, but they are. Right, so I can rewrite this to look more geometric if I pull the 5 away and multiply this by 1 over 2 and raise that to the nth power, right? That would be the same thing because 1 to the nth power is just 1. And then if I do the 2 in the denominator to the nth power, I get back the 2 to the n in the bottom, and then the normal 5. So in this case, my a1 term, right, if I plug in 1, I get 5 times 1/2 to the first. So that's going to be 5 over 2. My r value is 1 over 2. And then if I take the absolute value of that, right, that's still positive 1 over 2, and that's less than 1, which means that this is going to converge. Right? So we can say that the sum of this infinite series from 1 to infinity of 5 over 2 to the n is going to equal my first term, so 5/2, over 1 minus my r value. So that's going to be 5/2 over 1/2. So my denominators are going to cancel out, and the sum of this series is actually 5. Right? So overall, it's going to equal 5. Okay. If I look at my next one, right, I have an invisible 1 out here. My a sub 1 term is going to be 1 times 5/2 to the first, which is going to equal 5/2. And my common ratio is that 5 over 2 inside parentheses. Now 5 over 2 is 2.5, right? The absolute value of that is greater than 1. So this is going to diverge, right? So we say that this diverges by the geometric series test. Right? So as soon as that common ratio is bigger than 1 absolute value-wise, right, just diverges, we're done with the problem. So now in C, right, we have a geometric series where we have 5 times negative 1/2, all raised to the n power, right? Got my a1 term is 5 times negative 1/2, and I start at 0 this time, so I actually don't want to find a1, I want to find a0, and that's anything to the 0 power is 1, so I'm just going to get a 5. My r value is negative 1/2, and the absolute value of r, right, is positive 1/2, which is less than 1. So this is going to converge by the geometric series test. And we can say that this infinite sum, this series, right, just copying it down, it's going to equal my first term over 1 minus my ratio, which is negative 1/2. Right, so then I have 5 over 1 minus negative 1/2 is 1 plus 1/2, so that's 3/2. So that's equal to 5 times 2/3. So we're going to get 10/3 here. So overall, that infinite series goes to 10/3. Okay. Right. Almost done here. Right? So the last thing that we're going to do is look at what's called the nth term test for divergence. Emphasis on the word divergence there. So we have two theorems that go along with this. The first is called the limit of the nth term of a convergence series. So if we know we have an infinite series and it converges, then we know that the limit of the sequence must be 0. So that means eventually at the end of our sum, where all of the terms we're essentially adding our 0, which is why our sum goes to a finite value. Now, the actual nth term test for divergence is the contrapositive of that previous theorem, meaning you flip the order of the sentence and negate both parts. So now we can say if the limit of the sequence is not equal to 0, well, then the infinite sum, the infinite series must diverge, right? So if your sequence on the inside is not going to 0, your series automatically diverges. But you cannot say that if the limit equals 0, that it must converge. You cannot use this to prove convergence. So we want to be really careful about that. You can only use this for divergence. So we're going to do 4 quick practice problems, right? So if we look at these with the limit test, right, we can also, for part A, we could do that with geometric series, right? So if I look at the limit as n goes to infinity of 2 to the n, right, that's going to go to infinity, which is not 0. So we can say that this diverges by the nth term test. Right, if I look at the second one, right, limit as n goes to infinity of n factorial over 2 times n factorial plus 1, right, if I break that up, right, that's the limit. Right, if we think about this, right, in terms of that plus 1 on the end and the denominator is really not changing anything. So if we just look at it in terms of the big parts, right, same way that we do horizontal asymptotes, this is going to come down to equal 1/2. So that does not equal 0, so this also diverges by the nth term test. Right, if we have 1 over n, right, the limit as n goes to infinity of 1 over n does in fact equal 0. So it doesn't necessarily diverge, but it also doesn't mean that it converges. So we actually can't say anything here, so we're going to say that the nth term test is inconclusive. We can't prove convergence. And then I'm going to leave part D for your own experiment. So try and see if you can figure out if that's going to converge or diverge.